All right, everybody, this is Bill Corey again. We're going to continue on here with Basic Hydraulics 2, following the flow of the water through the pump. And last time we talked about how the pump was put together, the different parts of the pump. And today we're going to take a look at a couple different types of pump. We did mention last time centrifugals and submersibles, so we'll go a little more in depth in it today. So what we're going to start out with here is we're going to take a look at the curve. And as we look at the curve, you're going to notice the curve is nothing more than a chart, just a graph piece of paper. There's numbers in the bottom and there's numbers on the left-hand side. Those numbers in the bottom are going to represent your flow in U.S. gallons per minute, and the numbers on the left-hand side are going to represent your head in feet of water. Now, of course, this is not a real curve, so what I've done is I've gone into one of our catalogs and I pulled off a real curve, and you can see by this real curve that there's a little more information there. Again, on the bottom it still says U.S. gallons per minute. On the left-hand side it still says total head in feet. But you'll notice on the top, because we are a global business and we do a lot of stuff outside of the United States, we are also putting liters per minute on the top, and on the right-hand side we're using meters of head. So our newer curves are going to add those two things to it. But we're going to take a look at the older curve here, okay? Now, of course, how does the curve get produced? And so what we're looking at here is a picture of a pump. On the suction side of the pump, two pipe diameters from the suction hole, we are going to put something called a combination gauge. Now, there's a reason why we use what's called a combination gauge, because a combination gauge can read either pressure or vacuum. You can't have both, but you can have one or the other, and the combination gauge will read whichever one happens to be present at the time. So we are using a flooded suction. Because we are using a flooded suction, there is the probability that we are going to have pressure, especially when we do our shutoff head test. From that point, we're going to go another 5 straight pipe diameters for a total of 7 pipe diameters from that suction hole. So if my suction hole is a 3-inch hole, that means I'm going to go out 21 inches before I can do anything else. This allows for the water to get back in the middle of the pipe and gives us our best reading at our vacuum gauge. All right? On the discharge side of the pump, we're going to come out 2 pipe diameters. We're going to put a pressure gauge. This gauge is just reading pressure. Then we're going to go 5 more straight pipe diameters. We're going to put a flow meter. Someplace on the other side of the flow meter, we're going to put a valve. And that valve is there specifically to control the flow of the water going through the pump. Now what's going to happen is we're going to, remember we're using a flooded suction, so we're going to flood the pump. Of course, everybody realizes what you have when you have a pump that's not primed, right? It's called a fan, because all you're doing is moving air around. So when you're putting that, flooding the suction there, now we're priming the pump. So we turn the pump on, we get the water flowing through the pump, and then we're going to close the valve. When we close the valve, we're going to get a pressure reading right there at that pressure gauge on the discharge side. Now the question comes up, on the suction side, are we reading pressure or are we reading vacuum? And again, because this is a flooded suction, you're more than likely going to be reading pressure on that combination gauge. Remember that if there's pressure in the combination gauge, the pump did not create that pressure. So what we're going to do next is we're going to subtract that pressure from the pressure on the discharge pressure gauge so that we have just what the pump did. The last thing we're going to do is we're going to add in from the height from the pressure gauge to the combination gauge. It might only be inches, but we're going to add that in so we get a good accurate reading. Okay? Then we're going to go back to our pump curve, and at zero flow, we're going to put a point right there on our curve. And then, of course, again, based on the numbers in the bottom, this particular curve, you can see we've got 5 gallons a minute. We'll do the test at 10 gallons, at 15, at 20, at 25, and finally you'll notice at 29.5 gallons a minute and about 45 feet ahead, the curve just stops. Now, if you remember, last time we met, we talked about the fact of why this happens. And it happens because with the impeller diameter that we have, the RPMs that we're spinning it at, and the port width of that impeller, that's all the water we can get through there. At that point, we've reached suction failure. All right? Now we're going to ask another question. The next question we're going to ask is, can this pump do 15 gallons a minute at 150 feet of head? And the obvious answer is no, because you just barely have 150 feet of head at shutoff. Okay? So the next thought is then, will this pump do 10 gallons a minute at 100 feet of head? A lot of people here like to use the term yes, but the real answer is no. And the reason is, if I put a flow meter on there and I get the flow down to 10 gallons a minute, the pump will be doing 132 feet of head. If instead of using a flow meter I use a pressure regulator and I regulate the pressure to 100 feet ahead, the pump will be doing 20 plus gallons a minute. The key to remember here is the pump can only do the curve and nothing else. So what that means is, if I do put that flow meter on there and I do keep that flow down to 10 gallons a minute, I'm still going to get 132 feet of head. So people say, well, okay, fine, let's put a flow meter and a pressure restrictor on there, and we'll get 10 at 100. Well, that's true. From that point on, you'll get 10 at 100. But the pump will still be doing 10 at 132. So, of course, is there a way that we can make the pump do 10 at 100? And the answer is yes. That's why we brought it up. All right? How do we do that? Well, the two things that create the speed required to accomplish this task are the diameter of the impeller or the RPMs we spin it at. So one of the ways that we can change this pump to make it do 10 gallons a minute, 100 feet ahead, is to trim the impeller. However, we have to remember that should we trim that impeller, we're changing the whole curve by 32 feet, not just the 10 gallons a minute. What that means then is if I was actually running a system where I wanted to do 10 gallons a minute at one point at 100 feet ahead and 20 gallons a minute at another point at 100 feet ahead, I could never do the 20 gallons a minute at 100 feet ahead again because I've cut that 32 feet ahead off the system. This is why a variable frequency drive gets used, because the top curve there then represents our 3450 RPM, whereas the bottom curve now represents, say, maybe 2700. All right? So we've got 3450 on top. We've got 2700 at the bottom. And now, of course, any time that we want to, because we're using a variable frequency drive, we can go back and forth between 3450 and 2700, and that would allow us to change our flow and still maintain that 100 feet ahead that we want. All right? In our next slide here, we're seeing a cubic foot. A cubic foot is 12 inches high, 12 inches wide, 12 inches long. All right? If we were to fill that cubic foot with water, it would hold 7.486 gallons. You can notice there we've rounded it off to 7.5 gallons. Now, it's important that you remember fresh water, and I'm very particular in using that term fresh water, weighs 8.334 pounds per U.S. gallon. The reason this is so important for you to understand is because when we look at the horsepower formula, we note that the specific gravity of the fluid being pumped is used because the formula is based on fresh water. Now, of course, let's do the math. If we do the math, we take 8.334 pounds per gallon times our 7.486 gallons per cubic foot, and we wind up with 62.38 pounds of water per cubic foot. And that's what you can see we've got in our cubic foot here. Now what we're going to do is we're going to look at the base area. The base area is this bottom square. All right? You'll notice that it's 12 by 12, so we multiply 12 by 12 and we get 144 square inches. Now what we're going to do is we're going to take the weight of that water, we're going to divide it by the area of the square, and that's going to tell us for each square inch 1 foot high just how heavy that water is. And you'll notice that it comes up to be 0.433 pounds per square inch. Now, of course, one of the questions that I've gotten used to asking people is, does anybody ever talk or heard somebody say, oh man, if I just add that half a pound of water? And the answer, of course, is no. In our industry, we talk about whole pounds of water. So the question is, how do I calculate how high I have to go to get 1 pound of water? And the answer is, you divide 1 pound by 0.433. And when you do that, you're going to come up with 27.69 inches, which if you divide by 2.31 is going to be 2.309, we'll round it off to 2.31 feet of head. So 2.31 feet of head equals 1 pound of water per square inch. All right? That's our footprint. And those are the two numbers you need to remember. 2.31 feet of head equal a footprint of 1 square inch, 1 pound of water. All right? So therefore, since 1 psi equals 2.31 feet of head, we can take our psi times 2.31 and get our feet of head, or we can take our feet of head, divide it by 2.31, and come up with our psi. Now you're probably wondering, well, just where am I going to use this? And so we're going to talk now about something called total dynamic head, TDH. TDH can mean total dynamic head, or it can mean total discharge head. Remember, head means the energy content required to accomplish the task we want to accomplish. So when we look at TDH, you're going to notice here that we have a total amount of energy required to move a certain flow of water a definite height. That's what TDH is talking about. All right? TDH is made up of 3 things. Friction loss. We put friction loss up at the top of the page, up at the top of the picture here, so that way you don't forget it. It's very important. Now remember, the picture here is showing a submersible pump, but remember, this could be submersible, this could be above ground. The only difference is if it's an above ground pump, now we are also going to do friction loss on the suction side. Right below friction loss, it uses the term service pressure. And I want you to notice where service pressure starts at. It starts at the pressure tank, and it is measured up from that pressure tank to the highest point that I need to get that water. In our picture here, I've always kind of joked about, looks like that guy might be trying to get water on the top of his house before the fires in California consumes his building. So that might not be what it is, but it gives you the point. And the point is the water has to go so high. And that's what service pressure means, to have enough pressure to accomplish the task I want to get the water up on top of the house. Okay? Below service pressure, we come up with something that we're going to call pumping level. So total dynamic head or total discharge head is made up of 3 things: friction loss, service pressure, and pumping level. But I want you to know pumping level is also made up of 3 things. It's made up of elevation. Elevation is from the point at which the water exits the well to the point of usage. In our case, you can see there we've got a pitless adapter, and so we're coming out of the well and still going up a little bit further. A lot of times there is no elevation, but sometimes there is. So elevation is measured from where we're going to exit the well to that point of usage, in this case the pressure tank. Then we've got standing water level. Standing water level is measured from that same point, the well exit, down to the surface of the water with the pump turned off and the well fully recovered. All right? Now, in our last discussion here in Basic Hydraulics 1, we talked quite a bit about drawdown, because drawdown is the usable, where we're going to use the water from. So it's very, very important that we understand where that usable sense is. And of course, as that water table in that well drops until we get to equilibrium, we've got drawdown. All right? So now what we're going to do is we're going to take a look here looking at what we call pumping level. Pumping level is from the ground level, the well exit, to the drawdown level. Okay? That's our pumping level. Then pump setting, that's our pumping level. And our pump setting is going to be from the surface or exit of the well down to the pump. Basically, what pump setting is telling us is this is how much pipe is in the well. So that way we can calculate our friction loss. All right? Submergence, when it comes to submergence, we're going to recommend, because submergence is from the drawdown level to the pump, and we're going to recommend a minimum of 10 to 20 feet. Now, I know the National Groundwater Association strongly is going to encourage 20 feet. We say 10 feet. So you want to be at least 10 to 20 feet below the drawdown level with your pump. A lot of times people go even deeper than that, but this is a minimum requirement that we're going to suggest. And then the last thing we're going to look at here is that horizontal pipe run. It's very important that when you're talking horizontal pipe run, it doesn't necessarily mean just the horizontal. We're looking from the well exit to our point of usage, how many linear feet of pipe do we have? So that's what we're looking at there. All right? Now, the next thing we want to take a look at here is a jet pump. A jet pump is actually two pumps in one. You're going to notice that a jet has a nozzle, a jet has a venturi tube, and a jet has a body. All right? Those three things make up the jet. Some jets are going to be bolted on the front of the pump. Some jets are going to be put down the well. You'll notice if you look at the two jets on the left-hand side of the picture there, the one on the left-hand side is going to be suction over drive, and the one in the middle is drive over suction. All right? When you look at those two venturi tubes, you're going to notice that those venturi tubes look or appear to be round at the end. There's really a little notch in there, but they are totally round. And the reason they are is because when you take that venturi tube and you butt it up against the diffuser ring, that's got to form a surface that is going to seal so that way the water doesn't recirculate. And so that's why that's round all the way through. If you look at the one on the right-hand side, that venturi tube you can see has notches on the top. Those notches are strictly for a tool that we use to make sure that it gets torqued down properly, okay? But because it's not going up against the diffuser ring, we don't need to have it completely round on top, all right? We'll take a little closer look in a minute here how that all hooks up. So this is your designated shallow well pump where the jet is on the front of the pump. And when you'll notice here, when you're looking at this jet, you're going to see that there is a discharge side to the pump. And then if we look carefully, we'll also see that there is a suction side. So there's a discharge chamber and a suction chamber, okay? In the discharge chamber, we've got our impeller diffuser combination there. And what's going to happen is the water is going to come off of that impeller and it's going to go through the nozzle. And so you can see that there is an entrance to the nozzle and it happens to be in the discharge side of that chamber. Now, of course, nozzle indicates that it's a conical shape. And so you can see there that the opening where the water is going to go in, the discharge water goes in, is rather large. And where the water comes out, that's a rather small area. And so, of course, as that water comes out, what's going to happen is we are going to wind up with a higher velocity. So we've got a certain amount of pressure going through the nozzle, going into the nozzle. And of course, as that water comes out, it comes out with a higher velocity. Now, last week when we talked, we mentioned the idea of a nozzle, of a velocity and pressure. And of course, we're going to call this the mixing chamber, because as that high velocity water comes out, remember, as the velocity goes up, the pressure is going to come down. So we get this high velocity, low pressure water there, and that's what's actually going to pull water through the suction and into the mixing chamber. Now, as that water comes into the mixing chamber, we're going to mix the high velocity water with the well water. And as we do this, we're going to send it through the Venturi tube. As it goes through that Venturi tube, it's going to go into the impeller, and as it comes off the impeller, now it's going to either go out the discharge or it's going to find its way back into that nozzle. So there is a certain restriction that gives us pressure in that pump, so that way we can have enough pressure going through the nozzle to create the low pressure necessary to pull the water up. Okay? When we look at this next slide, it shows us a picture of a shallow well application. Now, it's very important, and we're going to get rid of this one picture. It's very important that you understand there's two wells there. So we're going to hide the one and just talk about the other. The other well that we're looking at there is called a driven point well. There is a water table. You can see we just put that line in there for the water table. And you need to remember that the point needs to be below the water table. If the point is not below the water table, you're going to wind up pulling air in, and you're going to really have a hard time priming that pump, if you can get it primed at all. So there's something called a drive coupling that goes on the end of the point. You're going to take a hammer and you're going to pound that down in the ground. Once you get the point far enough in the ground, you're going to connect another piece of pipe to this coupling, and you're going to put another drive coupling on, and you're going to drive it down some more. Of course, as you do that, you have to remember you have to use steel pipe. It's really hard to pound on plastic pipe and keep it together. So make sure that you're using steel pipe when you're going to use a driven point well. All right? There is going to be a check valve in the system also. The check valve is going to be out of the well. It is illegal to put a check valve in the ground. So it's going to be out of the well. You need to check with your local codes to see how far that check valve has to be out of the well vertically. All right? The reason that you want to get this check valve as close to the well as possible, however, is for priming purposes. You have to remember that from the check valve to the water surface is air, and that air has to be evacuated through the pump before the pump is going to prime. So, of course, the closer you can get the check valve, the better, the easier the pump is going to prime. All right? Now, we're going to get rid of that. We're going to take a look at the other well, so we'll cover up that driven point. Now, we're going to talk about a drilled well. When you have a drilled well, you're going to put a foot valve at the bottom of it. Now, the reason the foot valve is handy is because when you have a drilled well and you can put a foot valve in, that pump, when you prime it, is going to be primed all the way from the pump to the foot valve, which means it'll be much easier to get that pump to prime. You can use plastic or steel pipe either way. All right? Now, this is your deep well application. So that was a shallow well. Remember, shallow well, 25 feet to water. This is your deep well application. As you can see with your deep well application, the picture on the left, you're going to actually be sending water down that drive pipe. The center picture shows you that as that water goes through the nozzle area, you're going to find the nozzle increasing the velocity of that water, and that's going to open that foot valve and encourage the well water to flow in. And then, of course, in the last picture on the right-hand side there, you can see that water is now going to go up through the Venturi tube, and as it does, it's going to slow down. When it slows down, we're going to convert that high-velocity water into high-pressure water. Now, you have to remember, these were invented back in the 1930s. It gave people an opportunity to draw water from 100, 120 feet. Okay, prior to that, they could only get water from 25 feet, so this really was a huge improvement. All right? When we look at this next picture, it is going to be a deep well application now. All right. Now again, remember, deep well application can mean anywhere from 25 to 120 feet. The first thing we're going to do, of course, is we're going to get rid of one of the wells. Okay. And so we'll get rid of that drilled well there first, that 4-inch well. And we're going to work with what we call a single pipe. Okay, a single pipe system actually uses a 2 or 3-inch well. So they're only going to be used for 2 or 3-inch wells when you're talking single pipe. All right. Single pipe application also means that we are going to use a special adapter on the top of the well. And what that adapter is going to do is it's going to convert the drive water right down the well itself. So we'll use the well pipe as the drive pipe, and we'll drive the water down on the outside of the outside of the suction pipe. Then the water will go down through the hole in the jet body into the Venturi tube, back up through the Venturi tube, and then out. And as it does that, we're going to bring water back up. Now, once again, I'm going to strongly encourage you to use steel pipe when you're doing a single pipe application. The reason being is at the bottom of that well, you are putting a 2 or 3-inch jet. That jet has leathers in them, and the leathers are going to actually plug the well. So if you don't use steel pipe, when you go to pull that jet out, you might have a little difficult time. I had a guy call me up one time, and he said, I can't get the pump to prime. And so we spent 20 minutes talking about the jet, the nozzle, the Venturi, to make sure everything was right. And then he finally fessed up. The problem was he had a jet in the well and changed the pump out and wanted to put a new jet in. So when he went to pull the old jet out, because he had it on plastic pipe, it broke off. So then what he did was he took a piece of steel pipe, jammed it down the well, and forced the jet as far down as he could, and then put his new jet in. Of course, you have to remember, the bottom jet had a foot valve in it, and so did the top jet. And the problem was, because the jets were so far apart, he wasn't able to get enough velocity to actually lift up that bottom jet, and so basically he just plugged his well. He said, well, what do I do now? And I said, well, the first thing I do is go out there and pull that new jet out, and then you're going to have to call a professional and see if they can fish the other jet out of the well. If they can't fish the other jet out of the well, they're going to have to drill you a new well. The good news is you've already got a jet for it. Okay? Now, the next thing we're going to do here is we're going to get rid of all that. We're going to cover up our single pipe, and we're going to go to what we call a double pipe jet. When you go to a double pipe well, now you're actually putting 2 pipes right down the well. So that well must be a minimum of 4 inches in diameter. You can, of course, go to a lake or a pond, any open body of water, because you are using 2 pipes to go all the way to the jet, which means you have a totally enclosed system here now. All right? So what we're going to see now is we've got our jet down the well. Okay? 2 pipes going all the way down to that jet. Those pipes at this point can be steel or they can be plastic. It doesn't really matter. Okay? On the bottom of that jet, you're going to have a foot valve. Okay? and you're going to hook that drive water right directly up to that jet. Okay? Now what's going to happen is we're going to pump water down the drive water, and then we're going to pump it back up through the suction. All right? Now again, remember, they're only good up to about 120 feet. But there is something we can do, if necessary, so that we can use something deeper than that. So if we're living in an area where our water table tends to fluctuate, you can put in something called a tailpipe. Now, a tailpipe is a 35-foot length of pipe that's put on the bottom of the jet. All right? You need it to be atmospheric proof, so you want to make sure you got a nice solid piece of pipe there. If you're going to connect two pieces together, make sure there's a good tight connection there and no air leaks in it. Okay? What that does for you is a couple things. A tailpipe allows for the addition of one additional atmosphere. Remember, an atmosphere is 14.7 psi, 33.9 feet of head. So you've just given the jet the ability to go down another 25 to 30 feet. All right? Then we're going to take a look here at the next picture here, which is actually a picture of a series of pumps. When you put pumps in a series, the first pump determines the flow. All the pumps after just add head. However, when you place two or more pumps parallel, all right, each pump is drawing from the same source. What you're doing now is you're doubling your flow but keeping the head the same. Now, the only reason this is really important to us is because that basically is what a submersible pump is. It is a series of centrifugal pumps. All right? So this is one stage, or if you're talking about a bigger pump, this will be a bowl in which you are going to draw water through. Okay? It is made up of an impeller, the bowl or diffuser, and either an exit or a plate so that we can move the water up. All right? So the water is going to flow into A, which is the eye of the impeller. All right? The eye of the impeller is going to take that water. Now remember, what we're trying to accomplish here is increasing the velocity of the water. So the water is going to go in A, it's going to come out B. All right? B is the port, and that's where the water comes out of at an increased velocity. Then we send it through C, which is a diffuser, basically. And what the diffuser is going to do is it's going to take that high velocity water, slow it down, and convert that velocity into pressure. Then it's going to move it up. And again, depending on whether we're putting another bowl on top of that or whether we're putting the exit there, we're going to move up into the next bowl, the next eye of the next propeller, or we're going to move up into the exit of the pump. Okay? So it all depends on what we're trying to accomplish. This next pump that we're looking at here, this is a vertical multi-stage pump. It is a booster pump. Very important that you remember, this is a booster pump. What makes it a booster pump is the fact that there is a mechanical seal at the top of that shaft. And the mechanical seal needs to have water in it. So if you don't have this thing lubricated all the time, you're going to burn up that seal. And that's why we strongly encourage you to use it as a booster pump, because it is very, very hard to prime without burning up the seal. Okay? So the flow is going to come in, you'll notice on the left-hand side, and this is like having a submersible pump with an above-ground motor. And so you've got your stack of impeller, diffuser, and plates all put together there, and that water is going to move through each one of those. As it comes up through the discharge, now you're going to see that it's going to move between the stack and the pump, and then it's going to flow out through the discharge area. Okay, so again, this is primarily a booster application. I'll tell you honestly, if you go to our Beck program, it's going to say that this pump has suction lift, and it does. But again, your problem is trying to get it primed. Okay? Now, The next thing we're going to look at here is we're looking at a picture of an astronaut taking a spacewalk. And what's that got to do with our pumps? Well, the question comes up, how do we get the water into the pump? And so we're going to ask our astronaut here to do us a favor. Would you mind taking a pressure gauge with you and setting that pressure gauge at 0 when you get into what is considered deep space? Now, deep space is about 326 miles above the Earth, depending on where you're at, okay? So he gets up in a deep space. If he was to go out into that space shuttle there, and he was just dressed in street clothes, and he said, open the shuttle bay doors, he'd be dead, because the void of space doesn't like atmosphere. We've got atmosphere in our body, and so, of course, it would pull all the atmosphere out of our body, and we'd be dead. He, of course, knows this, so he puts on his spacesuit. Now when he goes out there and says, open the shuttle bay doors, when those doors open up, the void of space comes in on him again, but it can't get to him because of the fact that he's wearing his spacesuit. Okay? Now, of course, down there on Earth, we are protected also from that void of space. If we weren't, we'd all be dead. Since we're not dead, there's something protecting us, and what's protecting us is the atmosphere. Now, as I mentioned earlier, the atmosphere actually goes up 326 miles at the equator. And so, of course, you get away from the equator, it doesn't go up quite so far. There's 5 layers to the atmosphere. The area that we live in, or the area that we walk around here on Earth, is called the stratosphere. The stratosphere goes up about 40,000 feet. Okay? This is why when jets fly, they have these great big scoops on their engines so that they can collect as much oxygen that's up there. Remember, the further up you go, the less atmosphere there is. We talked about that last time. So, when the astronaut finally comes back down to Earth, and he's going to land right there in Cape Kennedy, he's going to give us that pressure gauge we gave him. What's the pressure gauge going to read? Well, the average weight of the atmosphere at sea level is 14.7 psi. So if we were to take 14.7 psi, multiply it by 2.31 feet of head, we would find that at sea level, there's 33.9 feet of head pushing down on the surface of the water. Okay? So we're going to go to a freshwater lake at sea level. We're going to put a 40-foot glass tube in that lake. We're going to put a support to hold that glass tube in a vertical position. You can see just inches under the water. Now what we're going to do is we're going to put a ladder on there. We've got a vacuum pump here, and we're going to connect the vacuum pump to the top of the glass tube. What we've just done is we've enclosed the atmosphere inside the glass tube. When we turn the vacuum pump on, the vacuum pump is going to evacuate the atmosphere out of the tube. As it does so, water is going to start going up the tube. The question is, how far does the water go up the tube? And the answer is, in a perfect world, 33.9 feet, because that's the maximum the atmosphere is pushing down. And so you can only go up as high as the atmosphere is pushing down. In reality, it'd only be about 33 feet, because you have to remember that all water, no matter what the temperature is, has a flash point where that water will convert from a liquid to a vapor. And the flash point for 70-degree water is about 33 feet. So when you get about 33 feet of water, it's going to flash from a liquid to a vapor. All right? You're going to notice here that the last 7 feet will remain vacuum. They cannot be filled. All right? So that's with a vacuum pump, but the question is, what kind of pumps do I make? I make centrifugal pumps. So the question is, how much lift do most people or most pump companies say you're going to get with a centrifugal pump? And the answer is 25 feet. So while a vacuum pump can lift water almost 33 feet, a centrifugal pump you limit it to about 25. And depending on the engineer you talk to, you may even go up to 30. Okay? So, how does it all work? Well, basically, remember, with our centrifugal pump, we have a very small area right there at the eye of the impeller that we're forcing the water to move through. As the water moves away from that area, it creates a vacuum. Remember, we've got atmospheric pressure pushing down the water, and it says, I'm going to fill that vacuum by pushing the water up to me. So as long as I've got enough atmospheric pressure, and as long as I'm creating a good enough vacuum, I will get the water to move from where it is to my pump, and I'll keep it moving that way. All right? The next thing we have to realize is this. As you go up in elevation, you're going to lose atmospheric pressure. All right? 2,000 feet is going to be about 1 psi. And so if we look at this chart right here, you'll notice it says at 2,000 feet, we're only going to have 13.7 psi. At 4,000 feet, we're only going to have 12.7 psi. At 6,000 feet, we're only going to lose 9/10, so we're going to be at 11.8 psi. At 8,000 feet, we're going to lose another 9/10, which puts us at 10.9 feet, or 10.9 pounds of pressure. Okay? If we were at Denver, remember Denver is 5,280 feet above sea level. So at 5,280 feet above sea level, you're going to see that we have a little over 12 psi pushing down on us. Okay? That's going to be important when we get into our advanced hydraulics. So don't forget that number. Now, this picture basically shows you how some of the terminology that you're going to have to use. All right? Remember that point right there, that imaginary line is drawn through the center of the eye of the impeller, is called the datum plane. The datum plane. On the suction side, from the datum plane to the working surface of the water, is called suction lift. Suction lift. When you get on the discharge side, from the datum plane to the highest point I have to pump the water, is called elevation. So when someone mentions the word lift, they're talking about the suction side of the pump. When they mention the word elevation, they're talking about the discharge side of the pump. And don't forget, horizontal run really means how many linear feet of pipe are there from my point of usage to my pump, so we can calculate all the friction loss required. All right? On this next picture here, what we're doing is we're going to divide the pump up, or the system up, into three things. The discharge side is made up of a pressure gauge and a gate valve. Now remember, we talked about doing the shutoff head test at the last training in Basic Hydraulics 1. And so what we're doing here is we're going to turn the water on, we're going to close that gate valve, we're going to get a pressure reading. If the pressure reading is what we believe it should be, then everything is fine. There's nothing wrong with the pump. All right? Now you have to start looking on the discharge side of the pump. Is there a broken main line? Is there a plugged main line? Did one zone not close all the way? And so now we're getting two zones turned on at once. That will keep that second zone from getting all the pressures required to give you the radius you want. So those are things you want to look at when the pressure gauge is saying what the pressure gauge is supposed to say. If the pressure gauge is not saying what the pressure gauge is supposed to say, then we know we got to look at the other area, which could be the pump. Now, of course, there's also a suction side, so we want to make sure that we've got that gauge in there. Remember, it's a combination gauge if I have a flooded suction. This particular picture here shows a suction lift, which means there's no flooded suction, which means if I really wanted to, I could use a vacuum gauge there. The vacuum gauge is going to tell me exactly how far off the water I am, and that's why it's important to have that gauge there. Don't forget, it is imperative that you support that suction pipe. If you do not have that suction pipe supported, with the length of that pipe and the weight of the water in that pipe, and that water's fluctuating a little bit, you can get that pipe to bounce up and down, and you're going to get things to break that you don't want to break. Remember also a minimum of 6 pipe diameters. Remember, the Hydraulic Institute said 7. We're going to cut you a little slack here and say at least 6. Okay? Keep the pump as close to the water vertically as possible. This makes the pump work easier. We saw that again in the last presentation. The pump is going to work easier when the pump is vertically closer to the water. And then the other thing we want you to remember here is once you get under the water, you want that suction to be at least 6 times the pipe diameter beneath the surface of the water. Again, what this is going to do, this is going to prevent whirlpooling. And as you prevent whirlpooling, it means that your system is going to work better. You won't be pulling air into the system. All right? Now, the next picture here, and this is going to be our last slide, is actually a picture of your house system. All right? And we'll just go through each one individually so we can see what's taking place here. All right? So what we've got is we've got our pump and motor. And again, this is if you're using a submersible pump. All right? Remember, you've got to get electricity down to that motor, so you're going to have an electrical cable down the well. All right? A lot of guys today use PVC pipe. As a matter of fact, some of them use that black plastic pipe. Whatever pipe you choose to use, you can use whatever you want. The key to remember, what most guys are going to do is they are going to tape that electric wire to the pipe. Whether it's plastic, whether it's steel, whether it's PVC, whatever it is, they're going to tape that cable to the pipe so that way it doesn't get nicked. All right? That's the whole purpose of it, is to keep that wire close to the pipe so it doesn't get nicked. However, there's another problem that can happen, and that's if you do not put a torque arrestor in play, you can get that plastic pipe to slap up against the well casing. And of course, if it slaps up against the well casing where that cable is taped right to the pipe, it's going to break that cable. And that's going to be another very difficult problem for you. And so to prevent that from happening, make sure that you put a torque arrestor in there. I really need to suggest that you use centering guides. I know that most professionals don't use them, but what the centering guides do is they kind of replace the tape. They keep that cable close to the pipe, and they also keep the pipe from slapping up against the well casing. So they are a very good value if you want to use them. Of course, one of the reasons why guys don't like to use them is they want to use that sonar gun, and it's kind of hard when you got plates in the way to get an accurate reading on your sonar gun. All right? The next thing I want to talk about here is called a check valve. Now, the check valve is there not for pump startup, but for the off of the pump. All right? There usually is a check valve built into the head of the pump. If not, you need a check valve within 30 feet of the pump. The other thing you're going to want to do is, if your well is more than 200 feet, you're going to want to put a check valve every 200 feet. And the reason that you want that check valve every 200 feet is because the fact that a 200-foot column of water weighs 90 pounds. So you're going to have 90 pounds plus water hammer on that check valve. Most check valves can handle that. You go 500 feet where now you've got 230 pounds plus water hammer, and you're knocking check valves out. Okay? The next thing up our list here is going to be a pitless adapter. Those of you from the southern regions, Florida, California, Arizona, some of those areas where you're sitting rather low and you don't get freezing, you probably aren't going to use a pitless adapter. Pitless adapters are used here in the north area where we want to go under the frost line horizontally from the well to the house. So we take that water, the pitless adapter is nothing more than a special elbow that takes that water from the vertical to the horizontal under the frost line. All right? We come to the top of the well, and we're going to put some kind of a well cap or well seal on there, all right? Hopefully you're going to allow for atmospheric pressure to get into that well, because remember, your pump is going to work a lot better if it's got atmospheric pressure pushing over the surface of the water, all right? You're going to come out of that well cap or seal with your electric wire. You'll go right back down the ground. Make sure that you put it in a conduit. That helps to protect it till it gets into the house. Once we get in the house, we actually have two systems. The first system is the electrical system. And I want you to know, even though what's pictured there is the disconnect switch, that is not where the electrical system starts. The electrical system starts at the main breaker box. It goes from the main breaker box to the disconnect switch. Now, of course, if you have a qualified electrician put that disconnect switch in, and he doesn't know anything about pumps, and he doesn't understand submersible pumps, he will give you a wire size from the main breaker box to the disconnect switch that gives you just enough amperage so you can run your pump if your pump is right there at the disconnect switch. Of course, if you're going to put your pump 300 or 400 feet away, that could cause a problem. So it's your responsibility to make sure that from the disconnect switch down to the pump motor, you have a wire size large enough to compensate for whatever the qualified electrician put in. As you come out of that disconnect switch, you're going to go to the pressure switch. Depending on the type of pump you're running will determine what you do next. If you have a 3-wire pump, you're going to go to a control box. If you have a 2-wire pump, you're just going to go right straight down the well. All right? So that's going to be your electrical system. Now let's take a look at our water system. In the water system, we have a pre-charged tank. And a guy told me one time, you can't call that a pre-charged tank. You can pre-charge any tank. And I said, okay, I want to make sure I understand what you're saying, because if I understand you, you're telling me that I can pre-charge an air-over-water tank. And he says, that's right. And I said, when it's not hooked up to the system? Because the bottom line is, if you pre-charge an air-over-water tank and then go to hook it up to the system, what's going to happen? You have to take the pressure off the system, out of the tank, before you hook it up. So I'm going to call mine a pre-charge tank because mine is pre-charged before I leave the factory, and it's still pre-charged when you hook it up. You, of course, are responsible to make sure that the pre-charge is set correctly, and that pre-charge should be 2 pounds less than the turn-on pressure. Now, simply put, if I'm running a 30-50 pressure switch, I want 38 pounds of air in that tank. If I'm running a 40-60 pressure switch, then I want 38 pounds of air in the tank. And if I'm running a 40-60 pressure switch, then I want, if I'm running a 50-70 pressure switch, then I want 48 pounds of pressure in the tank. If I'm running something bigger, well, you got to get a bigger pressure gauge then, because the pressure gauges I give out are all 50-pound maximum. Okay? Now, when we come out of that tank, we're coming out with something called a tank T. A tank T is a special fitting that has lots of openings on it, so we can add things in like that pressure switch or a drain cock. Now, the drain cock is there simply because of the fact that it is required to check the air pressure in the tank at least once every 6 months. If you don't check the air pressure in the tank every 6 months, what winds up happening is you lose your warranty. Because while tanks have a 5-year warranty, air pressure in the tank is not covered under warranty. So that's something somebody has to check. All right? When you're checking that air pressure in the tank, what you're basically going to do is hook up a hose to that drain cock, run it over to the drain, and drain that tank out. Now, of course, to do that, you want to disconnect that, you want to turn off that disconnect switch. All right? Of course, everybody likes to know how much pressure is in their system, so they're going to have a pressure gauge on that system. When you're checking pre-charge, that pressure gauge should read 0. So now you can take the top cover off the tank and you can check the pressure in the tank, and all you're checking is the pressure in the tank. If you've got pressure on that pressure gauge, when you check the air pressure in the tank, you're reading system pressure, not pre-charge pressure. Okay? The last thing we're going to talk about here is called the pressure relief valve. And as we get into talking about other systems, we'll come back and talk more about the pressure relief valve. But I do want you to know that my thoughts on the pressure relief valve are simply this. It is a very cheap and inexpensive insurance policy.